Right, so good evening everyone and welcome to class 6 of your CCNA course at CFSI. So during this class we'll be covering the second half of presentation 3 as we discussed in the last video. I hope you all were able to watch all of the last video. I previewed it mostly, and the audio and everything seemed to be fine. Let me know if the text is too blurry, and I'll need to turn up the resolution a bit. But from viewing it on my screen, it seemed to be fine, and the video quality and everything seemed to be acceptable. So let me know. I saw some feedback from some students already today, and they said it was fairly good, at least a lot better than the interactive session. So I think we'll be sticking with this for a while because our cases seem to be going up still, not down, and the government measures seem to be getting more harsher. So I expect that this will stretch into next week at least. So let me know. With all of your feedback, I will of course keep improving the video, and hopefully every video that I make and every class that goes on will be better than the last one. So yeah, let's get into the class for today. So last class we covered both of these topics here, 1.4 and 1.5. So yeah, you all should be seeing this here. So of course we're still in the network fundamentals section, so we covered all of these topics before, and of course don't forget, after every class, especially after the Thursday class, when you have the weekend and once you could find an hour or two in the whole weekend, look for this part of the topic. So I think it'll be numbered the same as well, 1.3 and then this topic name here. So try to look for this topic and in the textbook, and try to read Wendell Woodham's, he's the author of those books. Try to read his discussion on these topics. It will be a lot more in depth than what I cover. I try to stick to exactly what Cisco talks about here, whereas he tends to go into a lot more the nitty-gritty fine details, and some things that may not be fully relevant to the course, which could be overwhelming for some people, which is why I don't do it. But it is good if you want to go into the field, and just if you're confused about any of these topics, if you feel like I didn't go in depth enough, the textbooks really do go in a lot more depth. So really try to read up on these topics after we have covered them. So we covered interface issues and cabling issues last class, and comparing TCP to UDP. So you remember I showed this picture, which basically sums up everything we learned about TCP and UDP. TCP is a connection-oriented protocol. It's reliable. It delivers data in order, and it's basically used by applications that want to make sure that whatever they send is delivered exactly as they sent it to the receiver, of course with the additional overhead and the extra resources that takes, as opposed to UDP, where the sender just sends the data off, and however it finds its way to the receiver, it does. Whatever parts it takes, however much it's delayed, however much the data is rearranged along the way, as long as it reaches. And even then you don't guarantee that the data will reach. But it is a lot more resource friendly, and it's a lot lighter and simpler to implement. So both of these are used on the internet, of course, by different types of applications. And of course we went through some very common interface and cable issues. So we discussed collisions a lot more, and some of the different types of collisions that could happen on networks. We discussed some of those errors we see through our Cisco commands that can impact the higher layers. We discussed what duplex is and what happens when you have a mismatch in duplex, and how to fix those things. And the same thing with speed. What happens when you have a mismatch in speed, and how we can statically configure our devices to make sure that we never have a mismatch in duplex or speed. Right? So in this class, we will be going on to configuring and verifying IPv4 addressing and subnetting. I'll actually be doing it a bit backwards here. I'll be covering more of the subnetting and just general discussions on IPv4 addressing first, and then we'll touch on configurations after, because basically the whole of the CCNA is configuration of IPv4 addressing. We've actually done it already. Remember the first class where we set those IP addresses and the subnet masks on the laptops, and we had just had a simple two laptop to one switch, and we pinged the other laptop. That was configuration of IPv4 addressing. That is what we do basically in networking. But I will touch on it and show you an example and show you how you can apply subnetting and apply what you now know in IP addressing to the configuration. And because this subnetting topic is so large, this is basically all we'll be covering for this class. And in the next class, we'll go on to some of the additional topics in IP addressing. So private IPv4 addressing and IPv6 addressing we'll cover in the next class. Right, so let's get started. So topic 1.6, configuring IPv4 addressing and subnetting. So whenever you hear people talk about an IP address, a network address, or a layer 3 address, they are most likely talking about an IPv4 address. So I try to be very clear in what I'm referring to, because you don't just have IP addresses anymore, you have IPv4 and v6, version 4 and version 6 of the address. But still, in the vast majority of cases, people don't say IPv4, they just say IP. So if you hear people talk about an IP address, or a network address, or a layer 3 address, most of the times they'll just say IP address. They are referring to an IPv4 address. IPv4 is still, well, IPv4 addresses are still the most popular addresses used at the network layer, which is layer 3, to facilitate communications between networking devices. So for a lot of people, the whole of everything CCNA and everything networking, it works on IP addresses. They don't even know about IPv6, because IPv4 was and is still so popular. So what exactly is an IPv4 address? Well, an IPv4 address is a 32-bit number commonly written in dotted decimal notation using octets, which are groups of 8 bits in each group, to make 4 groups of 8 bits, 1 byte each. So that may sound complicated, but you actually know exactly what that means. For example, 192.168.1.1. So 32 bits, of course a bit is just the smallest unit of representation in the digital world. So you remember the graph from the last class where we showed the graphs going up and down, and we showed that those are literal voltages on the electrical wire, and that is how these hosts know information. They know how to transmit and receive information, right? So that those ups and downs, or sometimes the tops and the bottoms, depending on the implementation, those things translate to 1 and 0s. And a 1 and 0 is just a bit. A bit can be 1 or 0. That is it. So this address is composed of 32 of those bits. And instead of writing 101010000111, we came up with a more intelligent way of representing that number. So we took those 32 bits and we write those things in something called dotted decimal notation. So you see the dot here, dot, dot, dot. That is the dotted part of the decimal notation, and the 192.168, these are the normal decimal numbers that we know. And in this class we'll explore how we convert between those 101111, whatever it is, to our nice 192 or 168 numbers. So an octet is just a group of 8 bits, and then a byte is just a collection of 8 bits as well. And you see the 4 groups here, so you have 1 group there, 2, 3, 4 groups separated by dots. Yeah, so you're accustomed with this number, and I'm just explaining how we get this number now. Right, so let's break it down here. So dotted refers to the way in which each group of numbers are separated. Which each group is separated. So the dots, right? The dots are there, just the dot between the numbers. The decimal numbering system is the numbering system that we all use every day. It consists of digits made up of digits 0 to 9. So you may not even think about it, but our numbering system, the numbers that we use every day, is called the decimal numbering system. So there are many numbering systems. There's binary, which is 0 and 1, which is how bits are numbered, and that's the way computers operate. There's also octal notation, and there's hexadecimal notation. So you'll see different numbering schemes used in the IT world extensively. But of course, in our everyday use, we mainly use decimal notation, which is why they used it here, because we are accustomed to this. So the notation refers to the way in which a number is represented. For example, 2 to the power of 2, 1 multiplied by 4, and 4 all refer to the same numeric value, but they are represented in different ways. So you would have seen this in your mathematics classes. You know the values of all of these things, and you know it refers to the same number. It's just different representations. So it's the same thing in the numbering systems. So we have decimal numbering, the hexadecimal numbering I mentioned before, and now you'll know binary numbering. So it's all the same value, it's just represented in different ways. So now you can look at an IP address in dotted decimal notation, for example 192.168.100.1, and you can understand what is being referred to. So you know this is not just a number, you know the meaning of each of these numbers now and what the dots mean. Yeah. So this dotted decimal notation is used because it is easier for humans to read and remember. But of course, machines cannot read or perform operations on numbers in this form. So it is very easy for us to read this number and understand what it means, but a machine can't. So rather, a machine will read the IP address 192.168.1.1 in its binary equivalent, which is this long string of digits. So this and this represent the same value, but it's different representations. So this is the way that's easier for us to remember. This is the way that's easier for machines to remember and understand. So remember, this binary notation of the IP address may look intimidating, but it is the same value or number as before, just represented in a different form, a binary form, so that a machine can understand and process it. So to fully understand the CCNA/networking concepts of IPv4 addressing, we work in the binary number space. So as much as the dotted decimal notation is nice, to really understand the value of networking and understand how machines process them and what the numbers mean, we need to change from the static dotted decimal notation into the binary space. So it is therefore essential that you master both decimal to binary conversion and vice versa. So you need to know how to move between these two numbering schemes, moving from decimal numbers to binary numbers and moving from binary numbers to decimal numbers, which means converting numbers between the two forms we just illustrated. So let's first start with decimal to binary conversion. There are many methods to perform this, but we'll only be exploring one during class time. So this entire decimal to binary conversion topic, feel free to go on YouTube and look for a video on something else. Feel free to read up a textbook. Feel free to do online tutorials. You don't have to follow my method. And Cisco doesn't care either. They just care that you get the correct answer. And all of the methods lead to the same conversion. So if you don't understand the method that I'll be discussing in this class, feel free, go ahead and use another method. So know that the end results are always the same once the procedures are performed correctly. So feel free to explore other ways of performing this conversion. So use whatever resources you want. After this video, if you're still confused, feel free, go ahead and check out some other ways, any other YouTube video you could find on it. So this is my method. This is the method I use in my CCNA exam, and it was very easy for me. It was quick and easy for me to convert in the exam, and I believe Shiva recommends the same method, which is why we use it. It is just quick and easy, and in the exam you could convert like that. So very first step in this conversion. So we will first begin with this table. So this is the site that I used just for the tables and the images. Many other people will use the same method. So at the top here, you see the base of 2. So we actually start from here and we go backwards. So you see 2 to the power of 0. So we're starting with 0 and we go in that same 2, 2, 2, 2, 2, 2, 2. See the same base because it's a base of 2, which is how binary is written. So as long as we are converting to binary, and in machine language we always need to, we keep that 2 constant. So all we're incrementing here is that number on top. So we go 2 to the power 0, then 1, then 2, then 3, 4, 5, 6, 7. And we stop there because of course we only have a group of 8 bits between each dot, and we convert each group of them differently. Yeah, well, separately. So again, we just put our bases of 2, 8 of them. So you'll see we have 8 columns here, 1, 2, 3, 4, 5, 6, 7, 8. We draw out our 8 columns and we put the base of 2 there, and then we put the power of 0, and then 1, 2, 3, 4, 5, 6, 7. So 0 to 7 is 8 numbers in total. Then, of course, the decimal equivalent of those base of 2 numbers, we actually calculate it. So 2 to the power 0, anything to the power 0 is 1. 2 to the power of 1, anything, well, 2 to the power of 1 is just 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. 2 to the power of 6 is 64. And 2 to the power of 7 is 128. So this is something you basically just have to memorize. So for my exam, I memorized this top part here. I knew I just needed to write down in the exam 8 columns, and then these 2 from 2 to the 0 to 2 to the 7. And then from here, I just kept doubling. So if you multiply 1 by 2, you get 2. 2 by 2 is 4. 4 by 2 is 8. Then 16, 32, 64, 128. And that's why you get this top part of the table. Yeah? So for this example, so all we have so far, stay with me, all we have so far is this table and blank spaces below. That's all we have. And in the exam, this is all you're going to be writing. This top part here, and then the calculation for what these numbers actually represent below them. Yeah? So just for this example, to show you how we use the table now, we will be converting a normal number that we know, 192.168.1.2, which is in the dotted decimal form, to binary form. Once we have created our table, exactly as the slide before, we take the leftmost decimal number, the one in the leftmost octet, so him, in this case is 192, so leftmost, taking him first, and we start from the left of the table, using the decimal equivalent numbers as headers, right? So we start with him. So how many times can 128 fit into 192? So we start in here, left, 192, and then we start from the left of the table as well. So using the decimal equivalent numbers as headers. So we're not using these things, we're using the decimal equivalent numbers there, which is why we went down to this row. So we took our number 192, which was the leftmost here, and what we're asking now is how many times can 128 fit into 192? So this 128, we're asking how many times can this fit into our number here, which is 192. So of course once, right? You can't get two 128s and 192, but you can't get 1. So we get the ones there. So we therefore write 1 in the cell below 128 and subtract 128 by 1 from our number 192. So you see I left a space there and I just wrote it here. So think of it as a multiplication going down there. So we have 192, which is what we write here. We just take our number there and write it here. And then 128 can fit into 192 exactly once. So we write that 1 there. And then 128 by 1 is 128, and then we do a subtraction here. So 192 minus 128 is 64. Right? Everybody following? Take a break. Well, pause the video now and just follow through the text again if you lost. Just to go again, we took the number here, 192, and this is what we convert in first. So we took that 192, and then we start from the left of the table, using these decimal equivalent numbers here as the headers. So we took 192 and we ask ourselves how many times can 128 fit into 192, and the answer was 1. So we wrote our 192 here, and then 128 by the 1 that we just got is 128. So we have this 1 here, and then we did 192 minus 128 is 64. So this is our remainder that we carrying forward into the next step. Right, so all of that was one step. So we now repeat the process, moving right by one cell. So 64 was our remainder from last step, and that 64 can fit into 64, which is the next header here, exactly once. So remember, again, this was the remainder we took here. So everything else here, we leaving alone. The only thing we carrying forward into step 2 is this remainder here, which is 64. So we repeat this process. So 64, our remainder from the last step, can fit into 64. So this 64 here, exactly once again. So we wrote this 64 here. This 64 was the remainder from before. And what we're doing is taking this 64 here and asking ourselves, how many times can 64 fit into 64? And the answer for that is exactly once. So we therefore write 1 in our cell and we multiply again. So we had this 64 here, minus, and we put 64 by 1 is 64. So then 64 minus 64 is 0. So we leave in all of this here again, and this 0 is our remainder now. So we taking this 0 and we carrying it forward into the next step. So I hope you get any pattern now, right? So the only thing we brought forward here was that 0. So we repeat the process again. So we have this whole thing done, this whole thing done, and now we reach here. So we have 0. So 0 is what we brought forward, and we have 32 to contend with now. So how many times can 0 fit into 32? You can't, right? You have nothing to go into it. So 0 goes into 32 0 times. So for the first time now, we're writing 0 in this cell, because 0 cannot fit into 32 any times. So we write 0 in the cell and subtract 32 by 0, which is 0. So you see the 32, and we got 0 here because 0 can't fit into 32 any amount of times. And then 32 by 0 is 0. So 0 minus 0 equals 0. So you see, we write 0 in the cell, and then we multiply 32 by 0 to get the 0 there. And then we put 0 minus 0, because this is what we brought forward, and this was the result of this multiplication here. We subtracted both of them, and we get 0. So of course we have 3 columns filled now. We ignore all of this, and we take our 0 from here and carry it forward into the next step. So we repeat this process for the rest of the table, basically until all the cells here are filled, to get the full binary number for our first decimal number. So going back from the math, remember our number that we were trying to convert, our first decimal number ever, was 192. That was the decimal number that we were trying to convert into binary. So using this process, we can convert it. So we got the 1, we got the 1, we got the 0, and take the time now, and with the table that you draw, draw the rest of the table from here, and repeat this process, and see how you'll go. You should get this, because of course we only have 0 to work with. So we're going to get 0 straight down the board, which is why I didn't take the too many slides to complete it. You can see the pattern here. We're going to carry this 0 forward, and then 0 can't fit into 16 anytime. So we put the 0 there. 16 by 0 is 0. 0 minus 0 is 0. So we put the 0 there. We got a 0 again. We carry it forward, and we keep going like that. So take this table, write it down, and complete it for yourself. And you should get this binary number here. So these 1s and 0s that we wrote here are actually the binary equivalent of our decimal number. So therefore the decimal number 192 is equivalent to the binary number 11000000. Right? So we then repeat the same process above for our other decimal numbers, which was 168, 1, and 2. So remember, that was our number here. We wanted to convert this entire decimal number into binary form, and all we did with this whole table here, filling out all these cells, all we did was convert this 192, this first decimal number here, into a binary number. So once we are finished with that, we need to take this next number here, and then this next number here, and then this next number here, each with their own tables. So just for reference, so take your time, draw the same tables with these first two headers, and then take those numbers and repeat this exact same process. Ask yourself how many times it will fit in, and then put 1 or 0, then multiply, then minus, and then take your remainder and carry it forward. Go back through the slides for each step and try to do the conversion by yourself, and the reference is here. Yeah. So 168 is 1010 1000, and then 1, and then 2. So try it yourself and see if you get these numbers, and then once we get these equivalent numbers, we can write our complete number in binary. So if this doesn't make sense yet, just keep practicing. So pause the video now and see if you can get these numbers. Write the table down and follow the steps that I made, I don't know, around 15-20 minutes ago. Follow the same steps for these numbers and see if you could follow the same pattern and get these exact numbers. Right, so I hope you got these numbers. If not, feel free to message me in the group, and if I need to, I will take a piece of paper and I will write it down and I will show you the steps, or email or message, anything. I know subnetting is a very technical and mathematical concept, and a lot of people struggle with it. Of course, another way to pick this up is to find your own method. You don't need to master this method at all. Actually, when I learned the decimal to binary conversion, I used a long division method. And of course, the answer is the same, so it doesn't matter. Cisco isn't going to come and look for your table in the exam. They just want you to know how to do this. Yeah. So moving on. So take a pause and practice with these addresses as well. So figure out the binary equivalent for all of these addresses. And this is very important. These two addresses especially for the further topics in this presentation. So take the time now and practicing. And while you're practicing, think about this. What's the highest decimal number you can get in an octet? So in one of these groups separated by dots, what's the highest decimal number you could get? And what is the equivalent in binary? So what's the highest binary number you could get between these octets as well? Right? So these are the answers that you should have gotten. All of these here. And the highest decimal number that you can get is 255 or 255. And the equivalent is binary is 4 ones, of course. Because what can you get in a group of 8 bits besides 8 ones? Sorry, did I say 4 ones? Yeah, 8 ones, sorry. So you can't get higher than just setting everything to 1. So if anyone ever says an IP address with 256 in it, you know they're wrong. It can only go from 0 to 255, because that's the highest decimal number you can get. Right, so now let's switch it up. So instead of converting from decimal into binary, as we did before, we're going to convert from binary into decimal here. So to convert from binary to decimal, we simply reverse the process. We take the following binary number as an example. So 4 ones followed by 4 zeros. This is the binary number that we're going to convert into something decimal. We don't know exactly what yet. We just know that we're going to convert this. So we write this into the same table we made before. So remember our 2 to the power 0 and then 1 and 2, 3, 4, 5, 6, 7. And then we wrote the 1 here and then kept multiplying by 2 until we got 128, right in that exact same table. The difference here is that we're going to take our binary number and just write it in these cells. Remember, we got our binary number from these cells before, so we're now taking our binary number that we have and we're writing it into these cells. Then we simply multiply our numbers in each column and sum them at the bottom row. So 128 by 1 plus 64 by 1 plus 32 by 1 plus 16 by 1 plus 8 by 0 plus 4 by 0 plus 2 by 0 plus 1 by 0. So you see it here? So you have the multiplication here in brackets, and then we sum in everything between each column. And then the total summation of all of that is our decimal number. So our binary equivalent for this number here that we had originally is thus 240. Simple. So once you have the table memorized, you just throw the numbers in and multiply and add. That's it. Cool? So as we just discussed, practice makes perfect. So practice with the following binary addresses. What are their decimal equivalents? So of course, this would have just been the binary equivalent for one decimal number in one of those octets. So a full dotted decimal number is going to look like this: 8 bits dot, then next 8 bits, and the next 8 bits, and the next 8 bits. And of course, remember when we said a full IPv4 address is 32 bits. So you can see now how we have that as 8 bits plus 8 plus 8 plus 8, and 4 by 8 is 32. So we have a full IPv4 address here. So pause the video now and try to convert these addresses into their decimal equivalents. Right, so here are the answers. This equivalent to this is equivalent to this is equivalent to this, and this is equivalent to this. So you should have gotten the same answers. There are calculators online as well. If you're ever stuck and you ever need to know the correct answer, and you're not sure if you got the correct answer, there are decimal to binary converters online, and some converters can do it as well. Some calculators, sorry. So by now you must be asking, what's the point of all of this, right? Why do we need to know decimal to binary conversion? So to answer that, let's take another IPv4 address, 172.30.10.6. So this IPv4 address is actually missing a crucial bit of information. a network mask or a subnet mask. So network masks tell us how IP addresses are split between their network portions and their host portions. The network portion of an address simply refers to the network or LAN or subnet that the host belongs to. It must be the same for all hosts on a particular network or LAN or subnet. So what we're saying here is that an IP address is a half of a whole. You could put an IP address anywhere, but to really understand what the IP address stands for and to really understand the addressing, it is missing its other half, which is a subnet mask or a network mask. So what network masks and subnet masks do is they tell us how the addresses are split. So the IP address is actually not one complete number, but is actually could be split into two. So it's not two halves like exactly down the middle here. It could be moved somewhere through the number, and the two bits of it are called the network portion and the host portion. So a part of this address will be the network portion, and a part of it will be the host portion. So the network portion of the address is the part of the address that tells you the network or the LAN or the subnet that the host belongs to. So this is the same for all hosts on a particular network or LAN. So for instance, in your home network, if you were using, for example, 192.168.1.1, you'll notice that everything in your house will start with 192.168.1 dot something. So you have 192.168.1.1, then 1.2, then 1.3, and the reason for that is that they are all in the same network or the same LAN or the subnet. So that network portion has to be the same. Whereas the host portion, so the host portion refers to the part or the bits in the address that are changed for each host on the network in order to make that address unique for that host. This part of the address can never be the same for two hosts on the same network. So remember we said for the network portion it stays the same, so it's opposite for the host portion. For the host portion it changes, just to make sure that all IPv4 addresses are unique. So a complete IPv4 address is thus written as 172.30.10.6, 255.255.255.0 or 172.30.10.6/24. So remember we just had this 172.30.10.6, so now we put in on the subnet mask on it. So 172.30.10.6 and space and then the subnet mask. So this is the IP address and this is the subnet mask. So subnet masks look like 255.255.255.0. They could also look like slash something. So this 24 here is the same thing as this 255.255.255.0. So the first example simply writes out the IPv4 address and its network mask in decimal notation. So these are our normal decimal numbers as we just explored, while the second example writes it out in cider or slash notation. So it refers to the same thing, and we'll see why in a few slides. So cider or classless interdomain routing is the new method of working with IPv4 addresses. Many years ago, IPv4 addresses were regarded as classful addresses and could only be handed out in giant blocks as illustrated in the table below. So these giant blocks was how the internet was envisioned, I guess, a few years ago. Well, many years ago. So imagine it was 20 or 25 years ago. You could have gone to a regional internet registry and said, look, I want some IP addresses because I want to create a network in my business. And they would have said, okay, if you have a small network, take a block from this class C space. So your block of addresses might be 193.200.64.0, for example. Or they might say, look, you have a giant network like Google, and you're going to get 8.0.0.0/8. So you see that subnet mask there? That's the length of the address space. So class A were giant blocks, class B's were fairly big but smaller, and then class C's were the smallest, just /24s. Nowadays we don't have IP address space anymore, so we don't use classful addresses. So now with the advent of subnetting, we have broken these old large blocks up, and now addresses are written in cider notation like 172.30.10.6/24. So this is how you'll see addresses written most of the time. So to understand how we arrive at cider notation, let's first convert our IPv4 address and network mask above into binary notation. So we take in this same address here, and well, this same address here, this address, and this subnet mask, which you understand. So these are just dotted decimal numbers, and you know how to convert them into binary now, based on your new knowledge. Yeah. So to understand how we reach from here to here, we're going to convert into binary. In a second. Right. So to understand how we arrive at CIDR notation, let's first convert our IPv4 address and network mask into binary notation. So we had 172.30.10.6. So converting that into binary notation here, we break it up and we separate it by the dot still. Subnet mask, we take this and we put it into the binary form, separated by dot still. So to get our CIDR notation, we count the ones from the left of the subnet mask to end up with 24 network bits to create a CIDR mask of /24. Therefore, instead of writing 172.30.10.6 space 255.255.255.0, we can write 172.30.10.6/24. So you see the mapping here, right? 172.30.10.6, same thing here. We just copy that over. For the /24, we convert this into binary. So we converted this dotted decimal notation into binary, and subnet masks are always labeled, well, always written as ones from the right. So you'll never have a subnet mask with like 111100001111. A subnet mask can never have zeros anywhere. So it always has a certain number of ones from the left. So all we do is count how many ones we have from the left. So we count here, we get 8, then the next 8, then the next 8, and then we're done because we only have zeros here. So 3 by 8 is 24. So we write /24, and we therefore know what we mean. We could therefore, if we get this /24, we know it's 24 ones and then zeros to fill up the rest of the 32 bits. So we could write back this number and then convert into decimal notation again. So we could convert between CIDR notation and dotted decimal notation. Yeah. So now that we understand CIDR notation, let's explore the concept of subnetting. So subnetting refers to the process of creating smaller subnetworks from a large initial network. It is important to make more efficient use of our networks and our IP address spaces. Of course, because we don't have IP address space anymore. A lot of it is just done in the world because so many people are on the internet now. So considering our same example, we saw that the 172.30.10.0/24 network has 24 network bits. So we saw that here, right? We have 24 network bits there, or subnet bits. So since an IPv4 address always has 32 bits, so an IPv4 address will always have 32 bits. It must. So we know that we have the 32 bits, and then we know we have 24 network bits or subnet bits based on this subnet mask. So since an IPv4 address always has 32 bits, this leaves us with 32 minus 24, which is 8 bits to put host in. So it means 8 host bits. So the total number of host addresses creatable with 8 bits is just 2 to the power of 8, which is 256. So what that means is that in this network, this complete network, that is 172.30.10.0/24, we could fit 256 host machines in there. Well, not quite, but we could fit 256 host addresses in there. Because of this little math, 32 bits in total, and then 24 bits in the network mask or the subnet mask, which gives us 8 bits remaining to play with, which is 8 host bits. And then with 8 host bits, we could create 2 to the power of 8 different addresses for our hosts. Now, however, in most networks, the first address is reserved as the network address, which is a special address in the network called the network address, and the last is reserved as the broadcast address for that network. So remember we talked about broadcast. Just imagine somebody standing up and shouting to the entire class or to the entire group of people in a room. So the broadcast address is a way to address everybody inside of a network. So we need to reserve 2 special addresses in each network, the network address and the broadcast address. So this therefore gives us 256 minus 2, which is 254 usable host addresses. So you see how we got that? We had 8 bits, which we got from 32 minus 24 bits in our subnet mask. And with these 8 bits, we said 2 to the power of 8 is 256 total number of host addresses. then this part is standard. So in every single network, we have to reserve exactly 2 addresses, one for the network address and one for the broadcast address. That never changes in any size of network. And this therefore gives us 256 minus 2, that 2 is standard, and we get 254 usable host addresses. So therefore we could address 254 PCs or printers or whatever it is on our network. However, what if we don't need that many host addresses for our network? For example, what if our network only consists of one router, one office printer, and 10 office desktop PCs, which is a very popular small office, home office network. So in this network setup, considerable addresses would be wasted. This is where subnetting comes in. We can borrow bits from the host portion of our initial network to use as subnet bits. So every bit borrowed adds more subnets or networks for us to use, but subtracts from the host bits that we can actually use. So this means that the more bits we borrow to subnet, the more subnets we can create, but the fewer hosts we can assign within each network. So all subnetting operations need to be performed with our initial network address and our initial network mask, both in binary form. So in a nutshell, all we're doing here is we're taking one big network, and we realize we didn't need that big network because we just don't have that many hosts in this network. And we're going to take this big network and split it up into smaller networks, which is why it's called subnetting. We're making smaller subnetworks from a bigger network. Yeah? And you'll see some more math here now. So for example, consider that we wish to subnet the network 172.30.10.6/24. So this is our initial big network. We had previously determined the binary equivalent for both the host address and the network mask. Next, we perform a binary AND notation to determine our network address for this initial network. Remember we discussed network addresses a little bit before. We said that every single network has 2 special addresses. One of them is the network address. So now you're going to see how we get that special network address. So we perform a binary AND operation. So binary ANDing simply follows 3 rules. 3 very simple rules. So a 1 bit plus another 1 bit is 1, 1 and 0 is 0, and 0 and 0 is 0. So just remember those 3 operations. If you binary AND 2 1s together, you get a 1. If you AND a 1 and a 0, you get a 0. And if you AND a 0 and a 0, you get a 0. So we apply these binary rules to our host IPv4 address and its network mask. So you see, we had the 172.30.10.6. This is our host address before, and we converted it into this binary form. And then we got our subnet mask, which was this, and we converted this into binary form as well. So following the binary ANDing rules we just discussed, we end up with the following network address for this host and this subnet mask. So we did 1, we're going down on a line here, right? 1 and 1 is 1, 0 and 1 is 0, 1 and 1 is 1, 0 and 1 is 0, 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0, 0 and 1 is 0. And you keep going like that all the way. Draw lines if you have to, and keep ANDing, and you'll get this number here. So following these rules, we end up with this network address. And when we get this address in binary form, we could convert it back into decimal form. So you see now why the binary to decimal and decimal to binary conversion is so important. We have to convert here from decimal into binary, then we have to perform an operation in binary, then we have to convert back from binary into decimal. So this was our network address. And I know it seems long, but the more you do it and the more you practice, is the more you'll realize how easy it is and how quick you can do it once you have the practice. So this address here in decimal is our network address for the whole initial network that our host machine was a part of. The network portion of this address is highlighted in yellow, while the host portion is highlighted in green. So this is the network portion, this is the host portion. Remember, the network portion consists of the first n bits of our IP address, where n is the number of ones in our subnet mask. So you see, this was our subnet mask here. You're looking at this, all of the ones here. So how many ones do we have here? We have 8 here, then another 8, then another 8. 8 by 3 is 24. So therefore, the network portion here is going to be the first 24 bits, which we highlighted in yellow here. And then the last 8 bits is the host portion. because 32 minus 24 is 8. So see the last 8 bits here, they are going to be our host portion in green, and this is going to be very important now. So remember that during subnetting, we can only borrow bits from the host portion of the network. So I had a question in the last class, not last week, in the last iteration of the CCNA class, where somebody asked why we said we're borrowing bits. So we say we are borrowing bits because if we wanted to, we could return these borrowed bits and create our big unsubnetted network again if we wanted to. We're just borrowing these bits to create these smaller networks. So for example, if we borrow 1 bit from our initial network, so you see this is our initial network, and this was the network portion, this is the host portion, and we said we can only borrow it from the host portion. So we start from here. We can't mess with anything here, anything that we see in ones in the subnet mask, we can't mess with any of those. So we borrow 1 bit from the first bit here in the host portion. Yeah, so you see that bit in green there, that's the bit we're going to mess with. So with 1 bit, we get 2 to the power of 1. That 1 there is the 1 bit that we borrow, which is 2. So we can create 2 subnets using this 1 borrowed bit. So that's the math there. If you borrow 1 bit, you can create 2 to the power of 1, which is 2 subnets. So using 1 borrowed bit, you can create 2 subnets using that math there. So our first subnet address becomes this, with a 0 there. So remember the numbers that we highlighting here are going to be the numbers that we borrow. So first off, notice that we borrowed 1 bit to create our subnet mask. So that was the whole thing that we were doing here, right? We're creating subnets from our big network, and to do that we need to borrow bits from the host portion, and we're saying to start with we're going to borrow 1 bit from the host portion. We can't mess with anything here. We can only mess with these 8 bits here, and we started from the left. So we borrow 1 bit here, so that 1 bit there, remember this was our initial subnet mask with all of these 24 ones, which was /24, our initial subnet mask. Now we're borrowing 1 bit, so that /24 is going to become a /25. See, because we added in that 1 there, because this was the 1 that we borrowed, you see it manifests here. That 1 becomes a /25, our new subnet address. Same thing here. Remember we said we created 2 to the power of 1, 2. We created 2 subnets. So these are the 2 subnets we created. They have the same subnet mask there, and the difference in their network address is going to be here. So you see this 1 bit that we borrowed, the first network address is going to be this, our first subnet address becomes this thing. So we just copy this from our big network. So you'll see, if you go back, you'll see this whole binary bit there is this thing here, because we couldn't mess with this at all. So we just copy back that entire thing there, and then dot, and now we put our first borrowed bit here. So the first subnet address is this when it's 0, and the second subnet address is this with 1. Yeah, so this was the 1 bit that we can borrow. So the 1 bit shows up here, and then we put a 0 for the first subnet address and a 1 for the second subnet address. And then with these bits here, we're leaving these for our host portion because we only borrowed 1 bit. We had 8 bits to play with, we borrowed 1, which is why we flipped this to 1, but the other 7 bits are remaining as host bits. Yeah, and of course with our great binary to decimal conversion now, we can convert back to decimal. So you see there, we convert this whole thing into decimal, and we can convert this into our cider notation, and we change this to 1 now, and we convert this whole thing into decimal, and we can convert this into cider notation. And notice that the highlighted bits have changed. So we borrowed 1 bit, so we have 1 bit to play with. We could leave that as 0, and we could change this to 1, and everything else stays the same. So notice the highlighted bits. How many host addresses do we now have in each subnet? So we went from 8 full host bits to 7. So of course we can support less hosts in each subnet now. So we now have a subnet mask of /25, which means that we have 25 bits in our network portion. Of course the total number of bits didn't change. It's an IPv4 address, so it has 32 bits. 32 minus 25 is 7. So 2 to the power 7 is 128. This is our subnet block size. by the way, but just the first thing, 2 to the power 7 is 128. So this would be the total number of host addresses, but remember that you have to subtract 2 addresses to get the usable host addresses. So the number of usable host addresses is 126. 128 minus 2. Now this 128, the reason we don't just bypass this 128 and go straight to the 126 is because this is actually an important number. So this 128 here is our subnet block size. So just another way that some people do it, and you'll see the calculations if you look through a textbook or a video. They actually calculate this and they say this is your subnet block size or your network block size, and your first subnet address plus your block size gives you your second subnet address. So you see we had the 128 there, which was our subnet block size, and look at the decimal form. 172.30.10.0, 172.30.10.128. So if we take 128 and add it to this, we get the second subnet address. Second subnet address, without having to work in binary. So you'll see a lot of guides, or well, at least a few guides, doing it this way instead of doing it in the binary form. So you know to calculate the 126 usable host addresses now. So now, instead of one giant network with, remember we had 254 usable hosts before in one giant network, so we now have 2 subnets with 126 usable hosts in each network. Recall that we had 254 usable host addresses in the first subnet, on the first network. So you see we get 2 networks from one network, but we get less usable hosts in each network. Now let's repeat the process, of course. This is what subnetting is all about. So let's repeat the process instead creating 4 subnets. So 4 is equal to 2 to the power of 2. We therefore need to borrow 2 bits for this. So you see this bit of math, you will see Cisco ask these sorts of questions, which is why I put these seemingly random math equations in there. You'll see questions asking you to create 2 subnets or 4 subnets or 5 subnets, and you need to know how to do this math. You need to know the minimum number of bits that you can use to create your required number of subnets. So in this case, if we're going to create 4 subnets, we need to borrow 2 bits, because 4 is equal to 2 to the power of 2. This second 2 here is the number of bits we need to borrow. Yeah? So our first subnet address becomes this address again, there. So this is the same thing we borrowed. Going back all the way here. Same thing we copied. That we copied all the way here. And we put all zeros to start with. And in this case, I highlighted 2 numbers because we're borrowing 2 bits. So this was our first subnet address, and it's the same subnet address we have again, just copying it there. Now our subnet address changes, because instead of 24 ones here, we borrowed 2 bits. So we're extending this subnet mask into this bit here. So we're adding 2 ones into this. So remember we had a /24 before, because we had 24 ones. So now we're adding 2 more to that, because we borrowed 2 bits. So we have a /26, which is our new subnet address. So our second subnet address becomes this whole thing, which we just copy over from here, bring that right there, and then with these 2 bits that we borrow now, we're going to increment that by 1. So instead of 0, 0 for the first subnet, we go 0, 1, because 0, 0 plus 1 is 0, 1. And then we leave the rest of it as zeros, because these are going to be our host portions. We don't care about that right now. We're just calculating subnet addresses. And of course, with this binary that we just did, we could convert into decimal and get our second subnet address in decimal. And of course, these subnet addresses are going to be the same, because we're creating these fixed /26 subnets. Our third subnet address becomes this bit, which we just copied, and now we took the 0, 1 here. When you add an next one to that, you get 1, 0, because 0, 1 plus 1 is 1, 0. And then we could convert this into decimal as well to get our third subnet address, and then the subnet mask or the subnet address stays the same. Yeah, with these 2 added ones there for /26. And then finally, our fourth subnet becomes 1, 1. So we take this and we add a 1 against it. So you see we copy these bits, and then we add a 1 again to this, and we get this. And the reason we stopped there is because we only had 2 bits to play with. So we went 0 0, 0 1, 1 0, and 1 1, 1 1 there. When you have 2 bits, you can only get those 4 iterations. You can't do anything else with 2 bits because you can only go zeros and ones. So there are no other combinations that we could do with these 2 bits. So those are the only 4 subnet addresses we could get. And of course, we convert that into decimal. You get that there, and then it's the same subnet address there. So in this example, we borrowed 2 bits, thereby creating 4 subnets because 2 to the power of 2 is 4. In each subnet, we can now accommodate 32 minus 26, which is 6 host bits. So remember, we get the 26 from here because we added in 2 ones here. So we had a slash 26 and 26 ones here. Then 32, which is the total number of bits we have here, minus these 26 ones gives us 6 zeros or 6 host bits. 2 to the power of 6 is 64, which is our subnet block size. So we'll go back again. You see the 0, then 64, then 128, then 192. We just added 64 each time. So you can see how the block size is useful. Then to get our usable host addresses, we have to minus 2 from this block size to account for the broadcast address and the network address. And you can see the pattern now, right? So there's a lot more to subnetting there. So Cisco just wanted us to know some addressing and subnetting. There is a lot more to subnetting. If you're not seeing the pattern yet, go and practice. So I linked, subnetting practice is available here. I actually used this for my exam. I went on and I just took a piece of paper, well actually a book, and I practiced. There are a ton of practice questions in it at varying levels of difficulty. So you'll see it start off at very simple subnetting like we did here, and it will go all the way into worded questions and VLSM, which is variable length subnet masks, which means that you don't need to have all of your subnets as /26. You could have one as /24, one as /23, one as /29. Subnetting can get fairly complicated, but I don't want to spend 5 classes on this teaching all of those complicated things when it's literally half of one topic in the exam, and we have so many other things to cover. So I think this is enough for laying the foundation and making sure you at least know how to convert between the 2 types of addresses, and you know how to calculate the very important bits, the number of hosts and the subnet block size and the subnet portion. And now if you're still feeling unsure about this, or even if you're feeling confident, go to this site and practice. Practicing it is just going to be you writing in a book and getting these same things computed. How many usable host addresses you could have, what are the network masks, the subnet masks and the network addresses for each subnet, and go as complicated as you want. But don't spend your whole CCNA course studying this too much, because this is all there is in the topic. There is no more topics here that mention subnetting, which is why I took out a lot of the extra information. There was a lot more in the previous version of the exam, but right now it's just right in. That is it. And we aren't even done with this topic yet. So this one topic wasn't even just that. There is more. So 1 second. Right. So yeah, make sure you get this practice in. And just to wrap up here, I'm going to cover a bit about what they mentioned here. So configuring and verifying IPv4 addressing. So we will be doing this throughout the rest of the course and in the lab. You'll see a lot of configurations in the lab that you need to do. In lab, 1 second, labs. So in lab 5, which is the lab for today, it is actually appropriately entitled IPv4 addressing. So you will be doing configuration and verification in this lab. But just to cover it a bit in theory as well, this would have been the first experience, I guess, most of you would have had with IPv4 addresses, right? This little box here in a Windows machine. So now you actually understand what an IP address is and why there's that dot in between and why you can't enter, for instance, 256 in any of these, you understand why a subnet mask looks like 255.255.255.0, and you understand the significance of it now. The subnet mask tells you how the IP address is split between the network portion and the host portion. And the last bit that I want to get into in this class is the default gateway. So it's not strictly IPv4 addressing and subnetting, but it is very closely tied, and it is part of this configuration. So the example I got in my time was, think of a default gateway as the door to a room. So think of your network as the room that you're in. If we were in class, I would say think of your network as all of the students inside the class. Having students inside the class is fine. You could talk to the other people in the network. You could communicate with other people in the network fine, and you do all of that at layer 2. So you could do all of that without a default gateway present, but eventually you will want to leave the room, or you will want to talk to people outside of your network, and that's where your default gateway kicks in. So your default gateway gives you a chance, or gives you the way to get out of the room. Think of it as the door outside of your room. So whenever you want to leave the room, you need to go to the default gateway. Same way, whenever you have a host on the network that wants to leave the network, that host needs to go to the default gateway to get a route or a method of leaving the network, going out to the internet, basically, or to turn on the network. A very important rule in a default gateway is that the default gateway needs to be in your subnet. So remember I said, if you have a network like 192.168.1. something, and your subnet mask is 255.255.255.0, then your default gateway needs to be 192.168.1. something. So of course you can't see it as easily in decimal as you could in binary, but basically once you do the subnetting and you convert into into binary, you will see the first and the last usable IP in each subnet. So you'll want to make sure that the default gateway is inside your subnet. The DNS servers, we'll get into that in a bit, but DNS server is basically a way to resolve something like docs.google.com into a usable IP, which is why we always put it in. But we will have a next topic on DNS servers. So here you'll see hosts here, printer, hosts, all of these things on the same network, and for them to get out to the internet, they need to go to their default gateway, which is this router here. Usually default gateway will be the first address on a network or the last address, but it could be anything, and it just points you and it has a route out to the rest of the network. Alright, just took a little pause because I realized there was a small bit of subnetting that I forgot. It's not strictly subnetting, it's more of the further stuff that I mentioned before. So I'm not sure how in-depth Cisco is going to go with this version of the CCNA. From what I and a lot of the other instructors have seen, they seem to have pulled out a lot of the depth in these topics, and instead they've added more topics, so it's a wider breadth of topics but less depth into each topic. But just in case, I thought I should still mention some of the deeper topics. So just first, the answers will still be here, right, in this subnetting practice site. Let me make sure it still works. Right. Okay, good. Yeah. Right, so it does still work. This was designed for the older versions of the CCNA, but just in case, you should get familiar with these things. Right. Subnets of the size are possible in a class C. Right, so some of the questions may not be fully relevant to the current CCNA, but I have mentioned most of the answers, and anything you see missing from there, check the textbook or ask me. it is still useful information to know. It may just be that I didn't mention it because it isn't explicitly in this list of exam topics. But one thing I just remembered that I should mention, besides the table that I had a while back, let me make sure it was there. Right, this. Right, so Cisco didn't explicitly mention classful addressing and classless addressing, but you should memorize this table. This was a big deal in the last Cisco exam, so knowing the 5 different classes of addresses and the range of the different classes, so knowing that a class A starts at 0 and ends at 127, and then a B starts at 128 and ends at 191. Those were things that Cisco wanted you to learn, as well as the lengths of the subnet masks in each of these first 3 classes. So make sure you memorize this table there. And also, let me see, this is what I added in here. Right, so I added in some more stuff to these slides here, so it'll be updated by the time you're following along with this video. So we calculated some of the important concepts here, right? I showed you how to borrow bits and how to create subnets and how to calculate the amount of subnets you'll get and the amount of host bits you'll get and the block size and the amount of usable addresses. But many subnetting questions, like these here, they will also ask you for certain special addresses and ranges in the subnet, namely the network address, the first usable address, the last usable address, and the broadcast address. So we covered the network address already. So in this example, you see here, our first subnet address becomes this there, and the second subnet address became this. So we incremented the binary bit here by 1 and we converted it back to decimal, and this was our second subnet address. So we have the subnet address already, and we have the subnet mask. Sorry, I need to change this to mask. Right, mask. Let me know if there are any other small mistypes here and there. I'll fix it as we go along. Mask. Right, so yeah, these are the subnet addresses or the network addresses, and these are the masks, which remain the same. Right, we'll make sure I had it correct. Block size, subnet mask, right? Okay, so just in this example and the other examples, subnet mask. Okay, I'll do a quick look through and see if I see any more of those masks errors. But right, so the point, yeah, so the stuff that I added in here was how to calculate these things that Cisco may ask you. So we know that the network address or subnet address is calculated by simply converting our binary address for the network. So the binary address that we calculated by playing with those bits that we borrowed into a decimal number. So once you convert that back into a decimal number, you have your network or subnet address already ready there. Now your first usable IP address is obtained by simply adding 1 to that address. So for example, in our first subnet in the last example, so the first network here, so the first subnet that became this or this, so for example, in that first subnet, our subnet address was this, which we showed there already. Our binary is this. Our first usable IP is thus this. So you see the 1, so 0 to 1, we just add 1 to it. So it's the address right after the network address. That's our first usable IP. So you can't actually assign the network address to anything or the subnet address to any host. The first usable IP is the IP right after that. So you see, to get that address, we just incremented the binary by 1. And our broadcast address is obtained by first adding the subnet block size to the network address, then subtracting 1, or by setting all the host bits in the subnet to 1 and converting to decimal. So first I'll show you the kind of weird shortcut way that a lot of people will show you. So you take the decimal version here. So this is our subnet address, sorry. or our network address. We added the block size to it, which was 64 in this case, and then we minus 1. So you see here we had our subnet block size was 64. So we add that 64 and we subtract 1, which is 63. So it's basically like we adding 63 there. So you see 10.63. But the binary way to do it is to leave our 2 borrowed bits and our whole network portion here to the way they are, and set all the host bits to be 1. So we leave all these bits here as the way they are and as the way they should be in the network address, and we set all the host bits to be 1, and we get our binary our broadcast address there. Now again, just like the subnet address or the network address, our broadcast address isn't actually an assignable address. You can't assign it to a host on a network. Rather, our last usable address, so the last address that we can actually assign to a host, is the address just before the broadcast address, so the one just before this. So you see the 63 here, we just take away 1 from that, so we get 62. Or in the binary form, we subtract 1. So say we had all ones here, we just take away 1 from that and we get 0 there. Yeah. So you can see, I think I covered this before. You can see how the subnetting acts as a balancing act between the number of networks that we need to create and the number of hosts that we need to accommodate in each subnet. So of course, again, go and practice the subnetting at this site. And I'm not sure if there are any easier sites. Maybe not. But I know this one, basic subnetting. Yeah, same thing here. Yeah, you do have binary practice and stuff here. Right, so yeah. If you want to practice your basic binary to decimal conversion, you have some practice there, and then you have the basic subnetting here. So start off here and then see if you can reach here. I believe I included all of the relevant information in the presentation. Feel free to let me know if I forgot anything or if any concepts weren't explained too clearly, and I will put up a follow-up video re-explaining certain things or adding certain things on. I'll probably just add in some slides into this presentation and I'll create another video for it. Right, so that's it for this class. Make sure you go to do lab 5, which was IP addressing. Right, so IP addressing there. And in the next class, next week, we'll be covering some more network fundamentals course. Well, some more topics in the network fundamentals module, which is describing the need for private IPv4 addressing, and then configuring and verifying some IPv6 addresses and address types, and then we'll be verifying IP parameters on our favorite types of machines. Okay, thank you, and I will see you in the next class.